Hello students. Welcome to the YouTube channel, Physics Simplified. In this video, we will try to develop the concept of relative motion between two bodies by discussing various cases and corresponding examples. So, without any further delay, let's jump into the discussion. Motion is a combined property of the object under study, as well as the observer. It is always relative. The motion of a particle is described by using kinematical quantities such as velocity, acceleration, etc. These quantities are dependent upon the state of motion, as seen by the observer. So, when we define the motion of a particle, we assume an observer or a reference frame, relative to which the given particle is in motion. Thus, to understand relative motion, we need to know the concept of a reference frame. Reference frame is an axis system, from which the motion is observed along with a clock, attached to the axis to measure time. Reference frame can be stationary or moving. In simple words, a reference frame is a platform, or a physical object, to which our coordinate system is attached, and from where the observer observes motions, and takes measurements relative to it. In everyday life, that reference frame is the ground. For example, if we say that water is flowing, or wind is blowing, or a person is running at a definite speed, we mean that all these are relative to the ground, which we have assumed to be fixed. Let us consider another example. Suppose two observers A and B are sitting inside the two cars, while the third observer C is standing outside. We consider two cars are moving towards right, with different speeds. For the observer C, A and B appear to be moving towards right with different speeds. For A, B appears to be moving forward, while C appears to be moving backward. And for B, both A and C appear to be moving backward with different speeds. So, we find that when two observers measure the velocity of the same object, they get different results if one observer is moving relative to the other. The velocity seen by a particular observer is called the velocity relative to that observer, or simply the relative velocity. To find the velocity of a moving object relative to another moving object, let us consider two observers are watching a moving particle P from the origins of reference frames A and B. The frame B is moving at a constant velocity, vector v suffix ba, relative to frame A. The figure shows a certain instant during the motion. At that instant, the position vector of the origin of frame B, relative to the origin of frame A, is vector r suffix ba. The position vector of particle P, relative to the origin of frame A, is vector r suffix pa, while that relative to the origin of frame B, is vector r suffix pb. According to the triangle law of vector, we obtain from the figure, vector r suffix pa is equal to vector r suffix pb plus vector r suffix ba. By taking the time derivative of this equation, we can relate the velocities of particle P relative to our observers. Therefore, vector v suffix pa is equal to vector v suffix pb plus vector v suffix ba. This equation tells us that simultaneously different observers will record different velocities of the same body. So, we can write vector v suffix pb is equal to vector v suffix pa minus vector v suffix ba. Thus, if the velocities of two bodies, here the particle P and frame B, are known relative to a common frame, here it is frame A, velocity of one body relative to the other can be found. Let us consider, the observer of frame A is located on the ground. Since the observer of frame A is stationary, hence, equation 2 can be written as, vector v suffix pb is equal to, vector v suffix pg, minus, vector v suffix bg. Let us mark this equation as number 3. Vector v suffix pg denotes the velocity of the particle P relative to the ground, while, vector v suffix bg denotes the velocity of the observer of frame B relative to the ground. It must be noted that velocity of a person or an object relative to the ground is the absolute velocity of the object or person. So, vector v suffix pg and vector v suffix bg can be simply written as vector v suffix p and vector v suffix b. So, the main logical expression of equation 3 is velocity of a particle relative to a moving observer is equal to the vector subtraction of velocity of the particle relative to ground and velocity of the same observer relative to the ground. Now, by taking time derivative of equation 2, we can relate the accelerations of the particle p relative to our observers. It must be noted that, since the frame B is moving at a constant velocity relative to frame A, the time derivative of vector v suffix ba is equal to 0. Using the concept we have developed so far, if we consider velocities of two bodies, A and B, relative to the ground as vector v suffix A and vector v suffix B, then velocity of A relative to B is given by vector v suffix AB equal to vector v suffix A minus vector v suffix B. Similarly, velocity of B relative to A is given by vector v suffix BA equal to vector v suffix B minus vector v suffix A. So, relative velocity of a particle A with respect to B is defined as the velocity with which A appears to move if B is considered to be at rest. In other words, it is the velocity with which A appears to move as seen by B, considering itself to be at rest. Now we will consider the graphical method to find relative velocity. Let two bodies A and B be moving with velocities v suffix A and v suffix B respectively at an angle theta with each other. We can write the velocity of A relative to B using the knowledge of vector subtraction as vector v suffix AB is equal to vector v suffix A plus negative of vector v suffix B. Similarly, velocity of B relative to A can be written as vector v suffix BA is equal to vector v suffix B plus negative of vector v suffix A. When two bodies move at an angle theta with each other, then the magnitude of their relative velocity is given by under square root v suffix A squared plus v suffix B squared minus 2 v suffix A v suffix B cos theta. It must be noted that 180 degrees minus theta is the angle between the positive and negative velocity vectors. If we consider alpha as the angle made by vector v suffix ba with the positive vector v suffix b and beta as the angle made by vector v suffix ab with the positive vector v suffix a, then the directions of vector v suffix ba and that of vector v suffix ab are given by these two equations. Let us now consider relative motion for bodies that are moving independently. If two bodies, A and B, move independently in the same direction, relative velocity between them is given by v suffix r is equal to v suffix a difference v suffix b. This is equal to the magnitude of the vector subtraction of v suffix a and v suffix b. It must be remembered that the difference is a positive difference. Now, depending upon the location of bodies and the magnitudes of their velocities, this relative velocity can be the relative velocity of approach or of separation. If velocity of A is greater than that of B, and A is approaching or following B, this relative velocity becomes the relative velocity of approach. This is shown in the following figure. Since A is approaching B, the relative separation between the two bodies decreases with time. But, if B is behind A, and velocity of A is greater than that of B, the relative velocity becomes the relative velocity of separation. Since A is moving away from B, their relative separation increases with time as shown in the figure. Now we consider that the two bodies are again moving independently, but in opposite direction. In this case, their relative velocity is equal to v suffix a plus v suffix b. This is because the direction of velocity of one object is opposite to that of the other. Till the bodies do not meet, this relative velocity is the relative velocity of approach. But after they meet, the same relative velocity becomes relative velocity of separation or receding. When two bodies approach each other, their relative separation decreases with time. But when the same two bodies recede or move away from each other in opposite direction, their relative separation increases with time. We will now consider the relative motion between bodies, which are moving dependently. Let us first know what dependent motion is. Dependent motion is the case when a person is moving on the surface of a moving carriage train, or an escalator, or a conveyor belt. In dependent motion, it is very important to understand that, if the velocity of a person walking on a moving surface is given, then this velocity is the velocity of the person, relative to that surface on which he is moving, and not relative to the stationary ground. This moving surface can be considered the person's ground. Let us discuss and understand this through the following situations. Case 1. As shown in the figure, a carriage train is moving with a definite velocity. A passenger is moving on the surface of this carriage train with another velocity, and is observed by an observer standing on the ground. Let vector v suffix t is the velocity of the train, relative to the stationary observer on the ground. So, this is the absolute velocity of the train, and can be expressed as vector v suffix tg. Let the passenger be moving on the surface of the moving train with velocity v, and this is the velocity of the passenger, relative to the train, which is his ground. We represent this velocity by vector v suffix pt. We consider the velocity of the same passenger, relative to the stationary observer on the ground be vector v suffix p. So, this is the velocity of the passenger relative to the ground, and is expressed as vector v suffix pg. In order to find the velocity of the passenger, relative to the stationary observer on the ground, we need to consider this velocity triangle. From this triangle we can write, vector v suffix pg is equal to vector v suffix tg plus vector v suffix pt. Substituting the corresponding expressions, we can rewrite the equation as vector v suffix p is equal to vector v suffix t plus vector v. So, the velocity of the passenger relative to the moving train is obtained from the subtraction of the absolute velocity vectors of the passenger and that of the train. This is given by the following equation: vector v suffix pt is equal to vector v suffix pg minus vector v suffix tg. Let the passenger be walking on the floor of a moving train, in the direction of the motion of the train, as shown in the figure. The corresponding velocity vector diagram is shown in the next figure. Considering the direction of motion of the train relative to the ground as positive, we find the velocity vector of the train relative to the ground, and that of the passenger relative to the train are positive. So, the magnitude of the velocity of the passenger, relative to the ground-based stationary observer is obtained by the algebraic sum of the velocity of the train relative to the ground, and the velocity of the passenger relative to the train. Therefore we obtain v suffix pg is equal to v suffix tg plus v suffix pt. Let the passenger now be walking on the floor of a moving train, opposite to the direction of motion of the train, and is again observed by the ground-based stationary observer. The velocity vector diagram for this situation is shown in the second figure. Again, by considering the direction of motion of the train relative to the ground as positive, we find the velocity vector of the passenger relative to the train as negative. So, the magnitude of the velocity of the passenger relative to the ground-based stationary observer is given by v suffix pg is equal to v suffix tg minus v suffix pt. In our previous two cases, we considered the ground-based observer to be at rest. Let us discuss the situation when the ground-based observer is in motion with a velocity, say, v suffix og. Then the velocity of the passenger walking inside the moving train, relative to the moving observer on the ground, can be found from the subtraction of the velocity vectors of the passenger relative to the ground, and that of the observer relative to the ground. We have already calculated the velocity of the walking passenger inside a moving train, relative to the ground. So, substituting this expression, we obtain the velocity of the passenger walking inside the moving train, relative to the ground-based moving observer as vector v suffix po is equal to vector v suffix tg plus vector v suffix pt minus vector v suffix og. There will be 4 subcases under this category. In the first subcase, we will find that both the observer on the ground and the passenger inside the train are moving in the same direction as that of the train. In the second subcase, we will find that the observer is moving on the ground opposite to the direction of motion of the train, while the passenger inside the train is moving in the same direction as that of the train. In the third subcase, we will find that the observer is now moving on the ground in the same direction as that of the train, but the passenger inside the train is moving opposite to the direction of motion of the train. And in the fourth subcase, we will find that both the observer on the ground and the passenger inside the train are moving opposite to the direction of motion of the train. Let us now find the expression of the velocity of the passenger relative to the moving observer in each of the 4 subcases. The situation of the first subcase is shown in the figure. Both the observer on the ground and the passenger inside the train are moving in the same direction as that of the train. By considering the direction of motion of the train as positive, from the corresponding velocity vector diagram we find that both the velocity of the passenger relative to the train, given by vector v suffix pt, and velocity of the observer relative to the ground, given by vector v suffix og, are positive. So, the magnitude of the velocity of the passenger relative to the ground-based moving observer is given by v suffix po is equal to v suffix tg plus v suffix pt minus v suffix og. The situation of the second subcase is shown in the figure. As shown in the figure, the observer is moving on the ground opposite to the direction of motion of the train, while the passenger inside the train is moving in the same direction as that of the train. By considering the direction of motion of the train as positive, from the corresponding velocity vector diagram we find that the velocity of the passenger relative to the train, given by vector v suffix pt, is positive, while velocity of the observer relative to the ground, given by vector v suffix og, is negative. So, the magnitude of the velocity of the passenger relative to the ground-based moving observer is given by v suffix po is equal to v suffix tg plus v suffix pt plus v suffix og. The situation of the third subcase is shown in the figure. As shown in the figure, the observer is now moving on the ground in the same direction as that of the train, but the passenger inside the train is moving opposite to the direction of motion of the train. By considering the direction of motion of the train as positive, from the corresponding velocity vector diagram we find that the velocity of the passenger relative to the train, given by vector v suffix pt, is negative, while velocity of the observer relative to the ground, given by vector v suffix og, is positive. So, the magnitude of the velocity of the passenger relative to the ground-based moving observer is given by v suffix po is equal to v suffix tg minus v suffix pt minus v suffix og. The situation of the final subcase is shown in the figure. As shown in the figure, both the observer on the ground and the passenger inside the train are moving opposite to the direction of motion of the train. By considering the direction of motion of the train again as positive, from the corresponding velocity vector diagram we find that both the velocity of the passenger relative to the train, given by vector v suffix pt, and velocity of the observer relative to the ground, given by vector v suffix og, are negative. So, the magnitude of the velocity of the passenger relative to the ground-based moving observer is given by v suffix po is equal to v suffix tg minus v suffix pt plus v suffix og. Let us consider another case of relative motion for bodies moving dependently. In this case, we consider the motion of a person on an escalator, observed by a ground-based stationary observer. Let vector v suffix pe be the velocity of a person relative to an escalator. Vector v suffix pg be the velocity of the same person relative to a stationary observer on the ground, and vector v suffix eg be the velocity of the escalator relative to the ground, that is, to the ground-based observer. So, the velocity of the person on the escalator, as seen by the ground-based stationary observer, is the vector sum of the velocity of escalator relative to the ground, and velocity of the person relative to the escalator. So, vector v suffix pg is equal to vector v suffix eg plus vector v suffix pe. Therefore, velocity of the person relative to the escalator is obtained from the vector subtraction of absolute velocities of the person and the escalator. Let us now consider some subcases. In our first subcase, we consider the escalator to be stationary, and the person is moving on it. So, the velocity of the person relative to the ground-based stationary observer is the same as that of the person relative to the stationary escalator. In the second subcase, the person is moving up the escalator, and the escalator itself is also moving up. Considering the upward motion of the escalator positive, we find both the velocity vector of the person relative to the escalator and that of the escalator relative to the ground are positive. So, the magnitude of velocity of the person relative to the ground-based observer is equal to the algebraic sum of the velocity of escalator relative to the ground and velocity of the person relative to the escalator, and is given by v suffix pg is equal to v suffix eg plus v suffix pe. In our final subcase, the person is moving down the escalator, while the escalator is moving up. Again, by considering the upward motion of the escalator positive, we find the velocity vector of the person relative to the escalator is negative, and that of the escalator relative to the ground is positive. So, the magnitude of the velocity of the person relative to the ground-based observer is given by v suffix pg is equal to v suffix eg minus v suffix pe.